Good evening, everyone. Welcome to your Thursday evening tour around your celestial neighborhood. I'm Irene Pease, your friendly neighborhood astronomer, coming to you straight out of Brooklyn, where I've been, hunkering down for about a year. So, feeling a little punchy tonight, and that might come through. Sorry, not sorry. But just kind of celebrating all the space that's out there. And it might seem empty, but it turns out that it's really not. So, what's up with all that space out there? Is anyone using it? Let's hope they're making good use of it, especially for those of us who've been stuck in little New York apartments. Um, you know what I mean. So tonight we'll be using same visuals as usual. Right now you see open space in the background. You can find and download that for free at openspaceproject.com. And in just a moment we'll be switching over to Stellarium, which you can find and download at stellarium.org. So let's get to it, see what's up in our night sky, and then we'll visit a whole bunch of space. Very spacey tonight. Looking forward to it. So there's our glorious Brooklyn night sky in all its glory, all the labels there for you, like a museum, as it should be. And I wasn't really sure, where to go. If I was talking about space and emptiness and voids, I guess there's kind of a blank constellation that we could focus on. This is a really nice week for the month because we have our new moon coming up. So if you have dark skies, you'll also have like more moonless skies for the next week or so. I think we have a new moon this weekend. So that's something to look forward to. And also, it's kind of Messier marathon season. So there's a lot of cool stuff out there in the great big empty universe. 110 objects on Messier's catalog. And if you can find those, good for you. And if you can't, that's okay too. You're still a totally valid astronomer. Vesta, if you haven't had a chance, go ahead and check it out. I'm still working on it because I've been grading papers instead of astronomizing. But we looked at Leo last time. So we looked at this big backwards question mark in the night sky. And I think a couple weeks back we got to Gemini, like the twins. I hope we did. So we have like the two bright stars, Castor and Pollux up there. And then kind of between Gemini and Leo, which are, relatively bright. They both have like really bright stars in them. Castor and Pollux and Regulus are all like in your top 20, top 25 brightest stars in the night sky. But then there's this kind of void in between them. And believe it or not, there's another faint constellation in there. It's kind of like that void, like inside the winter triangle. So remember back over here, there was Orion, which we'll hear about in a couple weeks from Kuiper Cat. Looking forward to that. Between Betelgeuse and Sirius and Procyon, there's actually the invisible unicorn, but at least you have like some Milky Way running through there. Over here between Gemini and Leo, not so much. But if we turn on our little cheat sheet, you can see, oh yeah, there's a stick figure of a bug or something. I'm not sure what that's supposed to be. If you tilt your head, it kind of looks maybe like a bug. And if you have enough imagination, it's a crab. So that's Cancer, the crab, the crabby crab, skittling sideways or, I don't know, attacking the lion or something. Anywho, that's where we get the Tropic of Cancer. So that's like where the sun, I guess, used to be at one of the solstices. It's shifted a little bit because of things never staying in the same place for too terribly long. But we do have a really nice star cluster. Imagine that, a lovely star cluster in what would otherwise be a relatively blank part of the sky. And you can see it in a dark, dark sky. You can see it with the naked eye. So if you can see the Milky Way, the winter Milky Way, then you can probably pick out this cluster. It's called the Beehive Cluster or Persepi, M44, I believe, on your Messier list. So if you're doing the Messier Marathon, there's your beehive. But it's all kind of buzzing around. You imagine like a little swarm of bees. I don't know. Busy doing something, hopefully making honey. So yeah, a really nice naked eye object in a very dark sky. Little bit challenging in the Brooklyn skies, but nice in binoculars or a telescope. For a telescope, you want a wide field of view for very low power. So it's kind of big, not quite as wide as the Pleiades, but it's up there. So that's a fun thing to watch out for this week. The Beehive, that's happening. Um, and Vesta is still happening. So if you haven't had a chance to check out Vesta, do it now. Do it before Sunday when we're going to take an hour out of your day and return it in the fall without interest, which should be totally illegal, but don't get me started. Anyway, yeah, don't forget to change your clocks. Unless you're in Arizona, then never mind. Good for you. So that's the sky. So we can pop back over to open space and see, what's up in space. Oh, the open space. Yes. There we go. There's the Earth. That's in space. And I think I had some other things on my list. Oh, yes. Things on the list. So I actually wanted to start closer. Oh, let's go somewhere where it's almost autumn. I was planning to go to Australia last year. So maybe let's just pop down there because I can. So if you're on Earth right now, kind of making assumptions about my audience here, that if you like swing your arms around not too wildly or like take a deep breath, right, you're sucking in a whole bunch of air. We have this fabulous atmosphere thanks to Earth's gravity. It holds all this air near the Earth, all these pesky, energetic, gassy molecules that, would otherwise go flying around and zipping all over. And, then Australia would be oh so lonely. But yeah, so we have this wonderful atmosphere. And there's a lot more of it. It's a lot denser near Earth's surface. And I think sometimes we take the air for granted, right? Wow. Okay, we're really in the boonies here. Okay, let's pretend not. Okay. I broke Australia. Oopsies. So normally, even in Australia, you can't really see the stars during the day. That's just a fun open space effect. But near the Earth, we have this wild atmosphere. Like if you go bike riding or try to run through it, you could feel like wind in your face. That's air. That's stuff. So not just for breathing, but also for pressure and keeping you pressurized properly and whatnot. So we have, oh goodness, a lot of stuff. It's so I have a bunch of numbers here, and I'm going to try not to get too numbery tonight, but it's 10 to the 19 molecules per cubic centimeter. Ugh, that's a big number. So 10 to the power 19, so like 1 with like 19 zeros after it. So that's just a lot of zeros. That's in every cubic centimeter. So a cubic centimeter, yeah, that's like, I don't know, like your pinky, like the end of your pinky. All right. So that's a lot of molecules, right? So you wave your arms around and you're like, but it's mostly empty because I can wave my arms through it. Well, yeah, but try waving your arms through something denser. It doesn't go as well. So yeah, it's less dense than other things, like food, pizza, rocks, trees. But yeah, there's still a lot of stuff there. It weighs over a kilogram per cubic meter, right? So it's still less dense than a lot of other things that we see. Let's try to unbreak Australia a smidge here. But there's still a lot of stuff here. So if we look around, okay, so maybe not in Australia because the data is not available. It's like I found the one top secret place in the outback. That's great. But there's all this stuff here, right? Not just the solid, but I'm looking around at all the air. And then if we start to get further away from the Earth, right, we basically live at the bottom of an ocean of air. So think about the bottom of the ocean and how like pancaked you'd be if you were down there, because your body's not really built for that. But your body's built for being at the bottom of this ocean of air. And like if you go on an airplane, don't ask me how they work, but somehow they do. If you go on an airplane, then your ears start to pop because it's like a different pressure and they have to pressurize the cabin and clean the air and all that stuff. So even if you're like at the next layer above the lower atmosphere, above the stratosphere, if you get into the troposphere, even there, it's like it's already down to like 1,000th the pressure that we feel like at sea level. And I forgot to note my altitude. So like this is around 14 kilometers. If we get up higher, I want to get up to about 50 kilometers, 60. So actually let's go up to 80. So if I go up to 80 kilometers, if you can get 80 kilometers up above the Earth, you could be an astronaut. So up here, this is 80, a little over 80 kilometers. And you can see like the atmosphere, right? We can see the stars more because we don't see them so much during the day, you know, because there's like scattering in the upper atmosphere, Rayleigh effect, blah, blah, blah. But yeah, so up above a lot of that air, there's still some air up here, but not a lot. Well, this would be considered high enough to be an astronaut, but space doesn't technically begin until 100 kilometers. So I just passed it a little bit. So space, if you could jump up 100 kilometers, you'd be in space. You'd be a space cadet, right? So that'd be fun, right? So this is still very close to the Earth. But out here, this is, you know, considered space, and we have a lot of different types of space though. So that's what I kind of want to get into a little bit tonight, is like the emptiness of these different regions of space. Because, you know, very close to the Earth is like totally different than like way out between stars or galaxies or whatever. So three main regions that I want to try to talk about and just poke around a little bit are going to be interplanetary space, interstellar space, and intergalactic space, in that order. I made an outline and everything. So interplanetary space, we want to get a little bit away from our lovely planet. So let's say goodbye to Australia. Sorry, I didn't really mean to break you. And out into interplanetary space. So I'm not sure exactly how far away we have to be like, you know, technically full on interplanetary. But there's actually still a lot of stuff out here. So we think of this as being pretty empty, like being a pretty good vacuum. But the thing is, we've actually been getting really good at making vacuums on Earth, about sucking matter out of a region and just emptying it. So a vacuum is just kind of like the absence of stuff, the absence of matter. Like there's no matter there. So a vacuum can't suck because it's not a thing, right? So if anyone tells you vacuums suck, like any Germans, they're like, oh yeah, Staubsaugers. It literally means a dust sucker, which is kind of what it does, but it's a pressure differential. Anywho, so if you're out here, it's like a vacuum, meaning there's not a lot of stuff, but there's still stuff. So what do we have in interplanetary space out between the planets? Well, I guess there's other planets, but the planets are few and far between. We have, if anyone's ever seen a meteor shower, right? We have like little bits of dust, teeny tiny meteoroids, things that break off of comets or asteroids, and those might hit the Earth or hit other things in space. It's been known to happen. We have cosmic rays, whatever those are, apparently ionized atomic nuclei. So if you have, you know, just a random atoms that have had their electrons stripped off, so they're charged. So those are zipping around. Other subatomic particles, so like all the stuff you get when you crack open an atom, random protons, positrons, electrons. You know, it's like a chemist just like spilled a bunch of stuff somewhere and it leaked out. Now it's like zipping around the universe. That's not exactly what happened, but just pretend. There's little bits of dust, and what astronomers call dust is not like the junk under my bed, but it's like, you know, teeny tiny solid particles. So I remember how many atoms it has to be like a grain of dust, like 100 or fewer, or 1,000 or fewer. Very, very small bits of like solid matter. So more than just atomic particles or molecules. There's also some random molecules, even organic molecules out there. So all that stuff is like floating around between the planets in this interplanetary space, but it's just not very dense. So again, on average, about 5 atoms per cubic centimeter. So instead of like 10 to the 19th that you have like Oh, thanks, Brian. Yeah, so about 100-ish for dust. Brian's got my back. Um, so, like, remember you had about 10 to the 19 molecules per cubic centimeter, probably sitting where you are, assuming none of you are in space right now. But way out here, there'd be like 5. So you could count it on your hand. Like the number of atoms that you're counting on your hand, they take up way less space than your hand does. Like it take up a fraction of the space than the numbers that you needed to count them. Um, and the fingers that you're using to count these things. So not a whole lot of stuff out here. Um, and of course, some regions are more dense than others, like closer to the planets, and in their magnetic fields, you're going to get like more stuff, dust and whatnot, some plasma and like other charged particles whizzing around. Um, but if you think about like one thing I like to think about just to compare these kind of different regions of emptiness are looking at the space between the major objects. So here we have planets that are tens of thousands of kilometers or tens of thousands of, basically tens of thousands of kilometers across in most cases for the big ones. But then they're several light minutes or even a light hour apart from each other. So thinking about how tiny these pinpoints are compared to the space between them. So that's like several orders of magnitude between the size of the planet and even if we're looking at the outer planets. So the outer planets are bigger, but they're also further apart. So very, very small dots in this kind of ocean of what seems like emptiness. But remember, like every cubic centimeter, there's like 5 whole atoms ish on average, right? Yeah, and some of that dust and stuff, that's how we get, as Faisal was saying, that's how we get the zodiacal light. And if you're not a AAA member and part of the astrophotography group, I have to say, you missed out on a super awesome video that was shared by one of our members. George posted an amazing video that I've already shared with some other friends of the zodiacal light. So we'll talk about that whole thing another time, but check it out. Now is also a good time of year to see that. I don't think I can show that in Stellarium, so I haven't talked about it. But zodiacal light is also a good one. So yeah, it's some of this dust and random stuff in interplanetary space that allows us to see that. If we move out a bit further, we can see what we have in interstellar space. All right, so I think of interstellar space. I did the calculations at one point. I actually didn't do it this week because I was busy trying to grade papers. But I think that interstellar space, as far as comparing the space between the stars to the size of stars themselves, has like the greatest number of orders of magnitude between those two things. So size of stars compared to space between them. So like our sun is, I just had it, like a few, less than 1 million or so kilometers across, but then it's so it's like a few light seconds, maybe a few light seconds across, but it's light years to the nearest stars. So with Pi Day coming up this weekend, so if you're going to celebrate with daylight savings and Pi Day, fun fact about seconds and years, kind of back of the envelope calculation, or one that you can just store safely in your brain. A year is approximately pi times 10 to the 7th seconds. Right, so 10 to the 7th is about the number of seconds in a year times pi. So that's several orders of magnitude between like the size of stars that are a few light seconds across and the distances between them, usually a few light years apart. And granted, yeah, a lot of stars are different sizes. So out here, we're down to like usually 1 or fewer cubic centimeters, 1 or fewer atoms per cubic centimeter. And even in something really pretty like I was just thinking we'd go, but we're going to hopefully, I think Kat's going to take us there when we go visit Orion. We can actually see the Orion Nebula that a lot of folks might be familiar with. And even in the denser parts of that, you're still only going to have like thousands or tens of thousands of atoms or electrons per cubic centimeter. Yeah, on the order of a couple thousand, basically. Even in the densest parts of that, it's way, way less dense. It's many, many orders of magnitude less dense than the air around you right now. So we see all these pretty pictures of nebulae and things um, in the summer, for all of you, again, like doing your Messier marathons this month. You have like the Trifid and the Lagoon and all these fun things. But even in those, it's much, much less dense than what we have in the air around us. So pretty empty, but there's still a lot of stuff there. So even like what we consider high density, the highest density molecular clouds, where these pretty nebulae and things are, we're talking, yeah, only like 10,000 molecules per cubic centimeter. So that's all the space between the stars. But there's other stuff out there. There's gas, there's dust, there's more of that interstellar wind, which is, like cosmic rays and all those charged particles and stuff. And a lot of that extends like out, kind of, yeah, permeates all around the galaxy and is not just in the plane, but extends a bit above and below the plane of our Milky Way galaxy, which I think I have in here. Oh yeah, there's our galaxy. Oh, look at that pretty galaxy. Isn't that nice? So then we get out to Intergalactic Medium, which I find absolutely mind-boggling. So if we just move out for a little bit, just for, again, kind of our perspective of where we are, I'm going to kind of turn on and off some different data sets here. Sorry, this isn't all right. Exact. Okay, that's close enough. So if we move out a little bit, we have these green dots. That's part of our local group, quote unquote local. And then somewhere out here, there's blue dots. Oh, there they are, the blue dots. So those are also part of our local group. So this is still considered local. And you might see in here a little galaxy smudge. That's Andromeda. Right? So if we think about the size of just these two galaxies compared to the space between them, it's much, much, they're much larger, and that space is much smaller than like the size versus distance between stars. So these are, like 100,000 light years across, and they're a few million light years. So that's only like 1 or 2 orders of magnitude. So not a huge deal, right? Plus there's all these other galaxies around here. Right, so lots and lots of galaxies, but I mean, as you keep moving out, like there's all these galaxies, but then there's a lot of space as well. So one thing I want to try, and I'll see how well it works. We're going to come back in here, and I practiced this earlier, but it's still probably not going to work because every time I practice things, it just doesn't really seem to help. All right, so here's what we're going to do is. So normally I would take people through the Virgo cluster, but I've already taken y'all through the Virgo cluster, just it's been a while. I felt like doing something slightly different. So bear with me as I set up something slightly different. So if you're an observer out there, one of the super fun things that I know I've tried to find, and it's always kind of annoying because I feel like I should be able to see it and then I can't see it as well, I think, is Stefans Quintet. So that's our target for tonight. We're going to go visit Stefans Quintet if Irene can find it. I know where it is. I know where it is. I know where it is. There it is. Okay. So in order to do this, I'm going to try one of these, something like that. Oh. And then something like this. Close enough for government work. All right, so some of you might recognize the constellation Pegasus up here. So Stefans Quintet is kind of off. This is the, I don't know, whichever east, west, I'm totally turned around right now, edge of the square of Pegasus. So up in there, and just so that I can see them better, I'm going to try to turn on the actual dots that'll make it up. So we're going to use, it's not part of the local group. They're a little bit further away, which is why they're such a fun challenge to try to find. So I'm going to turn on a couple labels to help, and we're going to turn them on so we can see them all. And I'm going to turn on another fun thing so that it'll look pretty when we get there. And then we're going to take a little ride. Hopefully that'll do. Okay, so we're aiming for this stuff in here, those green blobs. All right. Trying to stay on track. And off we go. Just going to close this. And we are leaving the solar system. And we should leave kind of our local interstellar medium. There go the stars. I already lost which one I was supposed to be looking for. And and we're getting further and further out. So not those green spots, those are too close, but these green spots over here. Oh, these green spots. And let's see if we can't get right up in there. Okay. Yeah. Not too bad. All right. So if I make these just a little bit bigger, we can kind of see our intergalactic medium. So this was supposed to be the fun thing. We make the galaxies look bigger. Yeah, that's big enough. Try to get over to the green ones. Navigating to the green. So in groups of galaxies, like the Stefans Quintet are actually pretty interesting because we have a whole bunch of kind of interactions. And so those interactions kind of churn up like a whole mess of gas and plasma and other stuff. Oh yeah, here they are. Stefans Quintet. Not finding the number that I was expecting, but I promise this is basically them. So as these are kind of whirling and swirling and zipping around each other, these are magnified, by the way. This is a little bit fake, but it looks pretty. So as they're kind of whirling and swirling around, you get like all this other stuff turned up, like all the like gas and all the stuff that we saw was the interstellar stuff. Then that gets turned up into the intergalactic medium. Oh, actually, sorry, they're over here. Are these the 73s? Yeah, sorry, these are them. There's 73, 18, 80. So those are Stefans Quintet, if you can see those on there. So there's actually a higher density of intergalactic medium in some of these whirling, swirling clusters and all these interacting things. So a lot of what we saw, a lot we talked about from the interstellar medium, but isn't it kind of pretty to see them kind of up close and personal like? Yes, definitely. Very pretty. But there's more. So it turns out that even though the space out here is very, very not full. So I said it was like going to be maybe on average like 1 atom per cubic centimeter. So that's like per pinky size volume in interstellar space. In intergalactic space, it's like 1 atom per cubic meter. All right. So that's like a couple atoms in a car. Right. So very, very empty. So just there's basically what 100,000, a million, just kidding, 1 million cubic centimeters in a meter. So it's like 1/1,000,000th the density out here. So very, very not dense. And yet there's a lot of space, right? So if you look at the universe on a large scale, which hold on to your bacon, just whoa. We're going to do that in a moment here. If we pull out, yeah, there's all these dots are galaxies now. And I'm actually going to turn on even more galaxies and hopefully not break everything. Oh, yeah, that might be breaking things. Um, Turn on even more galaxies, and you can see this large scale structure that I've talked about other times, right? So you see there's areas that are denser with galaxies. Again, all these dots are galaxies, but there's also these regions where there's a lot fewer galaxies. So there's voids. So even compared to like, just the space between our galaxy and Andromeda, there's all these like voids and stuff that are much, much emptier, but there's just a large volume there. And so, like, one of the most mind boggling things about intergalactic space is that's actually where most of the matter in the universe is. Most of the baryonic matter, meaning most of the atoms. So, okay, we don't really understand dark matter. We're working on it. Dark energy, it's a totally different thing. But as far as like actual matter, like hydrogen, helium, that kind of stuff, the stuff that makes up hydrogen and helium, and the stuff that hydrogen and helium and other metals, we'll say, make up, most of that stuff is between the galaxies in our intergalactic medium. There's this thing, apparently it's called the WIM, the what is it? The warm hot, and I don't understand why it's warm hot, but it's warm hot intergalactic medium that's probably about 40% of all baryons, 40% of matter is like in these filaments in the intergalactic medium. And then another almost 40% is like cold diffuse stuff in the intergalactic medium. So there's these hot filaments with all kinds of stuff. And then there's cold diffuse regions of the intergalactic medium with almost as much stuff. And that's, if you're doing numbers in your head, that's almost 80% of all the matter. And then like the other 20% or even less, because there's different estimates. Some estimates say up to 46% is the hot stuff. So that leaves maybe 15%, 14% for the rest of us. So like all the stars and all the pretty things, that could be like just a tiny percent, like less than 20% of what's in the universe. So if you think that your apartment is small and, it has a lot of stuff in it, right? So I kind of look around, I think about space a lot. Like, I feel like I don't have a lot of space, but even if I had a lot of space, like, there's still so much more out there. And I guess just whatever seems empty actually isn't. So I don't know what to make of that. I'm just a little bit loopy from being stuck in this apartment for a year, but looking forward to not being in here at some point. So thanks for joining me on this little wander, this meander through some voids and some space and some not so space. Again, I'm Irene Pease, your friendly neighborhood astronomer. You've been watching Stellarium, which you can find at stellarium.org. And we also saw Open Space. That's what you're seeing in the background now. You can find that at openspaceproject.com. So hope everyone's safe out there. Clear skies. Don't forget to wear a mask.